Okay, test 1, 2, 3 is recording. Can you hear me? Testing 1, 2, 3. Testing 1, 2, 3. Good. Do I need to start the recording and record again, or do you need to check the recording, or this is good? We can start. I think we can start. Yeah, I think so. Okay. Okay, good morning. Okay, so today we start, let's say, the second chapter. It's about regression. If you notice on the course content page on Canvas, I placed some videos that are already per topic from a couple of years ago, in addition to the lecture videos. So these are just, if you look at those, because we use the tablet basically, so they add more details, just for your own advantage. Okay, so regression. Okay, so we'll focus on really today linear regression, and then in the next two lectures we'll talk about polynomial regression as well as regularized regression, and then we'll look at some of the ways to measure the performance. Okay, now what is really a regression? So by definition, remember the classification definition was really you have a set number of classes and you are really interested in telling if an input data belongs to which class, right? So by classification, you have two classes, you have multi-classes, then you have a multi-classification problem. In regression, we are really looking at a mapping. So I have my input data, right? So this is my input data in here, and I'm trying to come up with a model, and the model could be a function of this form, for example, that really fit this model. So basically, whenever I have a new data point, I can predict basically the whatever I'm interested in the Y. So in this case, the amount of sales per as the output, and then the input is the total rainfall. So it's really a fitting function. So one function could be this one here, right? And we can look at this function as the linear function, right? So this is a linear function. So what we need to find is this basically parameter in here, this this value, as well as this value. Once we have these two values, then I define my model, and that's basically my regression or linear regression in this case. Not all data are really linear. So this one we have a linear relationship, so I can really have a line describing, or I can fit a line to describe my data. The second one, same thing, is linear. And then the last one, I don't have a linear relationship, right? I need to figure out a nonlinear function that tells my data. And that's when we talk about polynomial regression models and regularized models. We'll look at nonlinear data in here. So again, it's very, very important to keep in mind what is really regression is trying to do and how that compares to classification, right? So we will split this, as I mentioned, for the linear regression into a simple model and then a general model. And then we spend quite a bit of time on the cost function. And then today only we try to solve this problem using what we call normal equations, right? So this is a closed solution. We can equate it, and then next time we'll replace this with a numerical solution, which is the gradient descent. But for today is a closed formula solution called normal equations, and we'll see how we can derive those normal equations. let's start with this example where I'm looking at certain countries in here, and I'm looking at the relationship between the GDP per capita and the life satisfaction index, right? And now you start to kind of plot this data in here. And now the question is, if you really want to model this and have a regression model, then you want to come up with an equation or a line equation that really tells you basically what would be the life satisfaction given a certain GDP as an input data. So there are multiple different ways you can really come up with such a model. So we have the blue one, we have the green one, we have the red one, and each one of them basically is defined this way. So we have a theta 0, we have a theta 1 for the slope, and then this is multiplied by the input data, which is the GDP per capita. Right? And now these are all possible fitted models, but you can tell basically the red one here is a very, very far off from the data. You can tell the green is really, the trend is really the opposite of the data is conveying to you. And then the blue one is really missing a little bit. So now we have this kind of idea of what would be a good model, right? So what would be a good model? So if we really apply linear regression, it will give us this kind of model, this kind of line for this data. So now we know that theta 0 will be 4.85, and then theta 1 will be of this value. That will be our fitted model that we claim that this is a good model. And then later on we'll talk about in what sense we are claiming this to be the better model than the 3 previous ones in the previous slide. Right? And that's really what our goal in here. Of course, this is a really simple problem because the input is just basically a single feature. But what if you have multiple features, like an n-dimensional data? And that's what we're trying to solve in the general sense. So we can, with this introduction about regression, we can really start to set up our problem just as we did in the classification chapter, right? So now we have n samples. Again, it's the same as before, capital N samples, right? And now for each one of these samples, we have a pair. So x1 here is basically a vector that really, this is the first sample, right? That's x1, but basically the length of that vector is p, right? So we have p features, right? So we have p features. Again, you can take the absolute value of the x and the y values if you have such data as features, but you can really have something more interesting as we saw in the classification chapter. And then we have the output as y1 in here. And the same thing, we have x2 and y2, x3 and y3, all the way to xn and yn. So we have all these samples in here. Again, xi, general, this is the I sample. It has basically p elements in the vector in here. And we label that as xi1, that's the first feature for sample I. xi2, that's the second feature for sample I. xip, this is the pth feature for sample xi. And transpose, we all deal with a column vector in all our discussion this semester. And especially this is coming from a space of length dimension p. Right? And now we have, for each one of these samples as input, we have a scalar output, yi. So this is just a single number. So xi has an output of yi. So now a linear regression model, by definition, we assume basically the relationship between this yi and xi is linear. Right? So that's basically the first assumption we are imposing in here. Right? Now, to really model this, because this relationship is linear, then we have the theta 0 plus theta 1 times the first feature plus theta 2 times the second feature, all the way to theta p times the pth feature for sample xi. This basically will give us an estimate of what yi look like, right? And then we can really write this as using vectors. We have theta 0, and then we have the transpose of theta. So theta has theta 1, theta 2, theta all the way to theta p, multiplied by xi as a vector. So this is column vector. After the transpose, this becomes a row vector, and then multiplying this times this vector in here, then we have theta 1 times xi1 plus theta 2 times xi2, and so on. Then I get basically my equation here on the left-hand side. And this is basically the model. So now we have an equation that describes our linear regression model. We have yi is equal to theta 0 plus theta transpose times xi. Right? And if we have n of these samples, right? Again, we are looking at n samples. then you really can write this basically for I equal to 1, I equal to 2, I equal to 3. And then we're really trying to come up with a system of equations. We are trying to figure out what would be the thetas that will give me the smallest error between the predicted y and the yi's. Is the setup clear? Okay. So now you put everything together, and now if we can really write the y as a column vector. So this is my output y, and then I have this is the first output, second output, this is the nth output. I have my samples. So this is an ith sample. This is one sample for my data. And now I can see in here I'm inserting 1, and you will see in a minute why I'm doing that. And then I have the first feature all the way to the pth feature. So now this xi dimension y is p plus 1, right? And you will see that we talked about this, but I will remind you in a minute. And then I have the capital X, my data matrix in here. I will have, I take the first vector. This is, I replace I with 1, right? So I have x1 and take the transpose. So basically my x, the first row is my first sample. You see that? My first row is my first sample. My second row is my second sample, and so on. My nth row is my nth sample. But basically I have ones in here, right? So I inserted these ones in here. And then I have the theta. I'm putting theta 0. And that's basically the reason I have these ones. Because I don't really want to write this one as y equal to theta 0 plus x times theta. I want to write it just in one equation, one matrix. So now if you look in here, this is the x, right? This is the theta. Now every time I multiply this row by that column, I have 1 times theta 0. So I always have the theta 0 that I had in the previous line, right? So if you look here, I always have that theta 0 there, right? Doesn't matter which y or which I am at. The next row, multiply this by that, then I will have 1 times theta 0, x21 times theta 1, and so on all the way to x2p times theta p, right? So I always have theta zeros in all these equations plus. So this way, basically, I inserted the ones in here, which is basically I'm setting the one before the first feature for any of this my data samples, and then I put the theta 0 inside this theta vector. And now I have again theta dimension is p plus 1, dimension for the xi's is p plus 1, dimensions for the y's is capital N because that's the number of samples. And remember, I have how many rows I have in here? I have n of these rows, right? How many columns do I have? P plus 1. Right? So I multiply this times that, then I would end up with n samples. Any question about this formulation? Yes.
So we have key data, right?
No, n data. The number of samples is very, very important. I always have n samples. So basically the dimension here, if you look at x, this is the first sample, second sample, this is the nth sample. Each sample is described using a vector of p features, right?
But yeah, but I'm talking about data. So there's p data, right? That's natural with the p number of p or
the features, yes. Because it's exactly so the p actually this if you look at this will become obvious from this equation here, right? What I'm trying to come up with, the relationship between the x and the y is linear. So I'm trying to come up with a weighted average basically of the xi, right? So these are the weights. So theta 1 is the weight for the first feature, theta 2 is the weight for the second feature, theta p is the weight for the pth feature, right? And theta 0 basically is the bias. We call it the bias, but it's really not to limit our solution to passing through the origin in this case. Okay, any question about this? Okay. So now imagine that now I figure out what the theta would be, right? So I have theta hat. So what's really theta hat? So now in the previous, in here, if I really can have a magic wand and then find the exact theta that will give me the exact y's, then basically I have a deterministic solution that's really very thorough, but we don't have that, right? So now the best we could do to find an estimate of thetas, right? That will give us an estimate of the y's. Right? So I have theta hat that I'm trying to find. That will give me an estimate of the y's, right? This y, we call it y hat. This y in here is not exactly the same as y, right? Right? If if it's the same, that's perfect. My error is 0, but I'm trying to kind of figure out how close I can make this y hat to this y. In other words, what would be the theta hat that will minimize the difference between y hat and y, right? So I could really write the y as estimated using the theta hat. So I have x times theta hat. Remember, before I had y equal to x times theta. Now I found theta, but it's really this theta will be theta hat, and now there is a difference between this value and this y, the true y. I will just call this basically and my epsilon, my error in this case. So now I can model my error in here as basically the difference between the y and the y hat, or the difference between the y and the x theta hat. Okay, you see that? Okay, so the same thing in here. Or what I'm doing, the y hat are my estimated, my predicted, my calculated y, right? They're not really the exact ground truth. There will be difference between them and the ground truth. That difference between y hat 1 and y1 will be epsilon 1. Okay, that will be the difference. Everything else in here is basically the same as before. Xi is the same as before. The x data, the input is the same as before. But now I'm just making my theta hat now, theta as theta hat, because I'm calculating these thetas. I'm trying to find what the values for these thetas. Okay, are we good? Yes. Okay, so let me solve it and look at it from here. So one more. Look at this equation here. So we agree that for y1, right, I will have theta 0 plus theta 1 times x11, right? Plus theta 2 times x12 plus all the way to theta p times x1p, right? Now, I could continue doing this. I could write it using this notation here, right? So I have theta 0 outside, and then I have this vector in here, which is the row vector, right? And then I have the column vector for the xi. Do you see that? So basically, my thetas after the transpose, I have theta 1, theta 2, all the way to theta p, and then I have my x11, x I call it 1, 2, all the way to xi p, right? Plus my theta 0. You see that? So now this will be theta 0 plus theta 1 times x11 plus theta 2 times x12 and so on. Do you see that? Ready? Now all what I'm doing, I don't want this. I want to have just one vector notation. So I could really insert this x0, theta 0 here. So this becomes my vector theta, right? But that means I have to add 1 here. So now I have theta 0 times 1 plus theta 1 times x11 and so on. So I get the same equation. You see that? And that is what we did in here. I do the same thing, but so now all that change requirement is just in the x's, right? So now each one of my samples, I will add 1. When I have the capital X, the matrix, so notation wise, small x with a bold face as a vector, capital X with a bold face as the matrix, right? So now I have my matrix. All the first column values will be 1 because of this addition. Does that make sense? Okay. So now that's basically what it's just notation. It's just easier to deal with. Let's see. So we go from here, this linear model, and now we start to look at if we have some calculations for theta hat, that will give me a y hat, and then we introduce the error, which is between the difference between y and y hat. Okay. Any questions so far? Okay. So now we have this equation here, right? And we know that basically the error is the difference between y and y hat, right? So now, just on the side here, if you look at, we use just the base rule, right? So the probability, remember, of our thetas given our data. And data pairs could be x and y, right? So x and y, the xi's and the yi's. These are my data points. So from base rule, this is equal to probability of my data given thetas times probability of thetas divided by the probability of my data. Right? From base rule. Do you remember this? Right? So now this is the likelihood, right? This is the prior, right? And we always basically look at this as the constant, just to scale things between 0 and 1. So we can really pick this anything, or we just ignore it, this one here. So this is basically a constant, right? Now, as you will see later on, the priors, are we imposing anything on the model? Right? Are we trying to make the model follow certain things, right? So this is up to us what we are imposing on the model, right? When we talk about regularization, right? Remember when we did basically the L2 norm of the model has to be minimized, right? Has to be less than a certain value. I can impose anything I want. For now, for just today's, we'll not really impose anything. We can just make this equal to 1, right? So now I have basically the likelihood in here. I can really calculate this probability of my data, the y's and the x's, given my model, right? One choice to make it easy, we make an assumption for now that the data is really being drawn from a Gaussian distribution. Okay, so my data is drawn from a Gaussian distribution. So in that case, I could rewrite this as the follows. I could rewrite that as in here, right? So this is the probability of my data in theta. Then it becomes just a Gaussian. I have 1 over square root of 2 pi sigma. This is the Gaussian variance, standard deviation, e to the power. And then I have my yi's. So I'm assuming that the yi's are being drawn from a Gaussian distribution minus the mean, right? So this is the mean value, right? If you look at this, this is the mean value. This is the weight. This is theta, right? Theta 1 times x1 plus theta 2 times x2 plus theta 3. So this is basically, this is the mean value for that yi, right? So this is the mean value. And then I have the 2 sigma square in here. I could really choose sigma to be 1, or I leave it, or calculate it, or I look at the data, I have an estimate from it. But the most important thing is always start from the base rule, again, as we did in the classification year regression. And now we didn't really have, this is the constant. We don't have any constraints on the model for now, on the priors. So basically this calculation here could be simply to say, let's just assume we can redraw this data from a Gaussian distribution, right? Now I have the mean, and the mean value basically given my model, which I have here, is basically just a weighted average of my input data. That's the mean value, right? And now when I have, what I have in here is basically this expression here, right? This expression here to describe basically my likelihood that I'm looking at. Any question about this formulation? So the assumption first, the relationship between x and y is linear, and that basically leads us to this equation here. The next assumption, we look at the base rule, we pick basically our data from a Gaussian distribution. So we can really formulate this using a Gaussian PDF, as you can see it in here. Questions about this? So these are 2 assumptions so far we have made, right? What else? We didn't really make any constraints on my model, right? No, the priors basically. I just picked to make them equal to a 1. Okay. Okay. So now I have this likelihood, right? But keep in mind, what I'm still looking for, I'm trying to figure out what these thetas are. I really am trying to figure out what thetas. I don't have these thetas. Again, my whole target in here is to find these thetas in here, right? So now, first of all, we need to figure out what will be the cost function, right? What are we doing, right? What would be governing us to choose this theta? So now let's look at basically this likelihood expression. First of all, let's look at, if you look at the whole data set, right? We'll just bring this, before even I just name it as a cost function. Look at this expression here, right? So now yi, like y1, is drawn from a Gaussian distribution. And then I pick y2 from Gaussian distribution. I'm assuming basically these are independent from each other, right? So y1 and y2 and y3 and y4, they are independent of each other. So that's the third assumption here, right? So IID, right? Identical and independent run variables from each other, right? So now y1, y2, y3, and so on, they are independent of each other. So now if I'm looking at what will be the likelihood for my n samples for everything that I'm looking at, because they're really independent of each other, then it will basically be the product of these likelihood probabilities, right? Because I'm looking at the probability of the likelihood of y1, right? And then I'm looking at y2, y3, but they are independent of each other. So I'm looking at the product of these likelihoods, that will give me the overall basically likelihood for my entire n samples or n data. Do you see that? Question about this? Okay, so now this is the product defined over n samples of the individual likelihood for the individual samples drawn from a Gaussian distribution, which means I can replace this with the Gaussian distribution equation from the previous slide. Right? Any question about this? Okay. As you'll see in homework 2, dealing with this basically is a problem. It's not really a good from a computational point of view. So we always like to go to the log of things, right? So I take the log of both sides. So the log of basically this likelihood for all samples, and then I look at the log of this. So I have the log of this product in here, right? So now the log of something multiplied by each other is the sum of the individual log, right? We know that, right? So now summation log of whatever I have left in between here, right? Anybody has any question about this part? You are doing this in homework too, by the way. Okay, okay. It's no shame to ask. I mean, if you haven't done it yet in homework too. So anyway, so it's very simple. Log of the product is basically the summation of the individual logs. Okay. Now the next thing is we'd like to figure out basically what we do next. So let's really split this out. So I have the log of this value in here, right? So I have summation over I1 to n of log of this. Basically, this doesn't depend on I. So basically, the summation will be just capital N, right? I'm adding a constant n times, right? That's the first one. Minus 1 over 2 sigma square, because I have log of e, right, to the power of this. So this basically becomes in front of it. So I have negative 1 over 2 sigma square. I have the summation of this thing in here, because log and the exponential will cancel each other out, right? So I'll end up basically with this equation here, right? Now this one here, if you're trying to maximize this expression, right? This is basically constant, right? Maximize this expression, I'm maximizing this. Or I could really, as we did before in the regression in the classification, multiply by negative and minimizing the negative log of the likelihood, right? That's exactly the same trick we did before. Either we are maximizing this or we multiply it by a minus sign. So I'm really minimizing the negative log likelihood, this expression. So now all the way, I have my likelihood. I wrote it this way. I took the log. I found this one multiplied by negative. And now the whole problem to find the status is to minimize this one here, right? Right. So this is what we refer to as the maximum likelihood estimation problem, MLE, right? It's a very, very famous, basically, solution. Maximum likelihood estimation is this equation here. Any question about this? So if you look at this carefully, what does this tell you? Remember, we started here, right? Bayes rule. We impose that the samples are coming from a Gaussian distribution, right? And they are independent of each other, right? And then basically what we did, we just put them together, right? We just put them together here, right? We get the log, basically just something like scaling, like just a function log. And then we get to this point. So if you look at this equation, what is this? Exactly, this is the sum of the squared errors. This is the true value, yi. This is what? This is yi hat. So this is really nothing but, I take the mean squared error. I'm taking yi minus yi hat squared, right? It's exactly the same, right? So we get basically to the same, the mean squared error solution through the maximum likelihood estimation. Any question about this? If you keep these steps basically where we are starting from and we are every assumption we make, what are the assumptions? Basically, you have like the three assumptions. The linear relationship between x and y is a Gaussian distribution where we're taking our samples from, and then these samples are independent of each other, right? Three big assumptions to get to this point. Okay. So now, if you look carefully, as I mentioned, the likelihood in here basically is nothing but basically the sum of the square error, right? the error squares. Yes. That's the likelihood, right? This is the likelihood, right? So now I want to maximize, basically, I can get the true data given my model. So I'm trying to maximize my likelihood. Can I really get the model, the data correctly given my model theta? Right? That's the likelihood. And that's why it's called maximum as here. That's the algorithm, maximum likelihood estimation. That's MLE, right? I'm maximizing my likelihood in this case. Okay. So now this is just a, I would say, a visualization of what's really happening. Imagine that you have this in your samples, right? And this is your model in the blue line, right? If you take the absolute difference between the sample and your model, you are projecting each one of those samples onto your model. Basically, if this is y1, then your estimation of y1 hat is this value, right? This is how much error you made, right? If this is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 9, right? This is my y9. This is my y9 hat. This is how much error I made, right? But now we are looking at this as what? As a mean square error, right? The difference, right? And square it. So in a way, we are really looking at this whole area, right? This is the difference error square, right? And we are really trying to minimize this whole area, right? That's the difference between the two, L1 norm to L2, right? So this is basically what we're trying to minimize in this case. This is kind of another visualization of what we are really trying to do when we are trying to minimize this cost function in here. Okay, there's the cost function. Okay, it happened that now our equation now becomes so focused on we come with a cost function, and we're trying to basically minimize that cost function because remember, we are maximizing the likelihood or we are really minimizing the negative log likelihood, right? So we are really minimizing this cost function to find what would be the optimal thetas in here. It happened basically this formulation here that we have a convex quadratic function, right? Which means that we can really find a closed form solution, right, for it, right? And we haven't seen this before now. Before we go to the derivation, I just want to remind you of these derivatives, first order, second order derivatives. Remember, this x and a are both vectors, right? So derivative of x transpose times a with respect to x is a. Derivative of a transpose times x with respect to x is also a. And this one is the same as what? I have x squared, right? I mean, this is x transpose times a times x is basically a plus a transpose then times x. So just remember this from linear algebra course. Okay. Keep these two in mind. Let's start from here. Okay. So the first thing I want to do, this is my equation, right? I'm looking at the mean square error, right? So I have yi hat minus yi, or yi minus yi hat, it doesn't matter. And then summation over all i's from 1 to n, and then I'm averaging over n samples. This is my function. I want to find basically, I want to minimize this error in here. I could write this because I have vectors in here, right? So this will become y hat minus y transpose, if these are vectors, right? Times y hat vector minus y, right? This becomes, if I'm writing them as vectors. So I get rid of the summation. This becomes basically my over 1, yeah, 1 over n, right? So I have no summation. These are vectors. Do you see that? Right? Okay, so the same thing. Now, I replace my y hat in here with x theta hat. I replace my y hat in the second term with x theta hat. Okay? Okay, so let's continue. I can really start to really multiply x theta transpose times this x theta. I get the first term in here. X theta transpose times y. I get the second term. I have y transpose times x theta, third term. Y transpose times y. I get the fourth term in here. I can really simplify this, just get rid of the parentheses. So this will become theta transpose times x transpose, right? So x times theta, all transpose is the same as theta hat transpose times x transpose. I have it here. Same thing in here. This becomes theta hat transpose times x transpose, which I have it here. And then I have this term as it is, and this term as it is. Are we good so far? Okay. Now we take the derivative. of this function with respect to theta, which means I take derivative of the individual terms with respect to theta, right? Now, if you look at the first one, I have theta hat transpose times x transpose times x times theta hat. If you look at it here carefully, this is the same one. We have the second order derivatives, right? So I have x transpose and x, and I have some matrix in the middle. What's that matrix? And happened to this in this case, I have x transpose times x. This is a matrix, right? This is a matrix. Right? So this is the matrix in here. I have theta hat transpose. I have theta hat in here. So from the previous slide, we know that basically the derivative with respect to theta, which is the one, the outer terms, will be taking this term as it is, plus the transpose of the term. So transpose of this will be x transpose x, which is identical to this, and then times theta hat in there. Any question? Simplify this is basically become 2x transpose x, and then I have the theta hat in here. So the first term, derivative with respect to theta, will give me this one here. Any question about this? That's basically using the second order definition here for derivatives. And then for the other two terms I have in my equation here, basically I have this one and this one. Basically they are used the first order. So the derivative of the first one, which is theta hat transpose times x transpose times the y, with respect to theta, will be basically this term, right? Derivative of this term in here with respect to theta will be the y, the transpose of this. So y transpose x, all transpose, which will be x transpose times y. This is again the same term. So both of these terms, the second and the third, right? They have the same derivatives with theta, which is this one, right? And now finally, the fourth term, which is y transpose times y, it doesn't really depend on theta. Derivative of this with respect to theta will be a 0. Okay, I add them all together. I have 2 x transpose x theta for the first term. Then I have the second term and the third term. They have the same. So I have 2x transpose times y, and then I have 1 over n from here. That will be basically my derivative so far. Any question about this? Okay, I equate this to equal to a 0, right? As if I am equating this term to be equal to 0, because the capital N, I multiply both sides by capital N, I get this term, the 2 will cancel out, and now I can really multiply by x transpose x inverse from the left, on the left-hand side and the right-hand side. And now I have a closed form solution for theta hat, which only depends on the x, then the matrix, which is basically the matrix that includes my data, and the ground truth or the predictions from the ground truth sample. So all what I have in here is coming from the ground truth, from my training set, right? This is a closed form. So we refer to these as normal equations that will give us a direct or a closed form solution for our thetas in here. Any question? Just to recap, we started from the Bayes rule. We didn't make any assumption about the model, right? We treated the data as basically the probability here is constant. We have the likelihood, and to maximize the likelihood. First assumption, x and y have a linear relationship. Second assumption, my data samples are coming from a Gaussian distribution. These samples are independent of each other, right? And now when I try to maximize that likelihood, I ended up with basically a maximum likelihood estimation, which is a mean square error maximization. And now it happened to be a quadratic convex function. I can take the derivative with respect to theta. I go through the derivations, and now I have calculations or a closed form solution, a formula for theta hat in this case. Yes.
Just want to confirm that because we're assuming that that epsilon and like the possibility for all ID, right? That he doesn't do that multiplication.
Yes, exactly. Yes, yes. That you're referring to this one here. Yes.
That means because
Yeah, for the n samples, right? Because they're independent of each other, right? So the likelihood of the first sample and the first, second sample and the third sample and basically means multiplication, right? Okay. Again, the derivation in here, or what we need are these two derivatives, first and second order derivatives in here. Okay. So now we have a closed form solution or a formulation for, we call it normal equation from now on. Basically, homework 3 will deal with this. We'll just call normal equations. You know exactly what we are referring to. We are referring to what we have inside that blue box. Right? So one way, yes. What's what? Oh, what's the likelihood? This is the likelihood, right? Remember when we had in the classification, the example when we have you're gonna play outside as your output, right? Yes or no, like this classification is rainy, windy, like that, right? And we have a like very detailed what the likelihood is. In a nutshell, basically the likelihood is this, right? The probability of my data, right? My pairs, X and Y, right? Given my model, right? So now if I give you this model, if it's a really, really good model, right? Then basically I'm really having a very good estimation of what the data is. I want to maximize this capability, right? I want to maximize this capability if I have really a good model. If I have a bad model, then the likelihood I have this really calculated really well is very bad. So I have a huge error. So we're trying to maximize this expression. This is the likelihood. This is what we're trying to do. My pairs, my pairs of data, like the X and the Y, given my model, theta, right? That's what I'm trying to maximize in this case. So another way to look at this, and this is just from really a signal processing perspective, one way to look at what we are really trying to do, just to visualize this into the subspace, right? So now imagine that, or just let's look at this. So we have our X samples, right? So our N samples, these are the Xi's, right? So my capital X in here, the first row is sample 1 with a 1 concatenated basically at the very first. Second row is my second sample, P2 is my sample. We always have this assumption, right? And this has to do with the capacity of your model. The number of samples is larger than the number of features, right? If the other way around, then basically there is an issue with the model in that case. You don't have enough capacity to model the data, right? So now, what we are really looking at, we are looking at the subspace, right? So we have this X as a P by P matrix. And then we are claiming basically this one here is really defining a P plus 1 or just a P dimensional linear subspace, and is as an illustration, if you have 3, so I have X1, I have X2, I have X3. That's my subspace. I mean, maybe you heard this before, but basically if dimension is 3 or P is equal to 2 in this case, then I have this, my data is defining basically a subspace, right? That basically is with the 3 Cartesian coordinates, X1, X2, and X3, right? So my three features, right? They are really defining this 3-dimensional space. Any question about this? Okay. So now imagine that I have, this is the Y, right? And now what we are really saying is we are taking basically a projection, right? We are really, our solution here, as our solution is nothing but we are really trying to estimate this Y hat in here, right? Where basically it lies in this linear subspace that's really as close as possible to my Y hat, right? So we are really kind of to projection of this Y into this Y hat, right? So basically that's the green one is my space that I'm really defining at my solutions at, right? If my thetas, again, where this green came from, this is basically where it's coming from with the theta hat, right? The theta hat is telling you your solution in this subspace, because remember, X1, X2, X3, this is the whole subspace where the X's are coming from, right? Now, where are the Y's in there, right? So basically, I'm looking at this as a linear combination of X1, X2, X3, right? So that will be basically what? A plane in this subspace, right? That's the first assumption. It's a linear combination of the X's will give me the Y. So it has to be a plane or a hyperplane in my space. Now, imagine that basically that just I did the calculation for certain X's and Y's, and basically gave me this solution to be the optimal solution, right? This is the green one, right? If I give you Y, right? If I give you a new pair, I'm telling you basically, I don't know what X1 is, but the point is here, your solution to project this Y into what? Into this solution, right? Right? You project the Y into this solution subspace or solution hyperplane. This becomes your Y hat, right? So now you have the error between Y hat and Y is basically what you are really trying to minimize. Oops, in here, right? So this is the error you're trying to minimize. But you're trying to figure out if you have a lot of these x's and y's, you're trying to create this hyperplane, right, to minimize the error between the y and the y hat. Do you see that? So basically, it's nothing what they're doing is just basically projecting into this hyperplane. In other words, all what we are doing in normal equations in here, this is nothing but a projection matrix, right? Just a projection matrix, right? Fourier transform is what? Is also a projection, right? You're projecting from your data into your frequency domain subspace. In here, the subspace is defined by what? By the x, right? By the x's. All what they're really trying to do, we're trying to do a projection of my samples into basically some formulation, which is the projection matrix in this case. And we are trying to minimize that error in here, right? Okay. So now, why we call it normal equations? Because this fact in here. We can view this basically as orthogonal. It has to be orthogonal, right? So we do the projection here. This angle in here between the hyperplane and the projection has to be 90 degrees, right? It's orthogonal to the hyperplane. So basically that's where the name coming from. Normal equations in here is normal to the hyperplane, and that's basically the orthogonal projection that we are really referring to in here. Again, I mean, if project any data point, even the x and the y to the x, then you're looking at what? Orthogonal to the x-axis, right? The same thing in here, just in 3D, projecting this to this hyperplane, this between the hyperplane and this projection is so the error is orthogonal to the solution subspace. You see that? Again, this is just illustration to help you understand what we have done. What we did in here, just derivation of everything, and now here, just an illustration of what will really happen, right? You can actually start from the mean square error definition here, make an assumption about the y hat, just the mean value and the Gaussian, you can arrive at the same solution. Same thing in here. Okay? Any questions? Okay. So you did this and homework 1 a little bit, and then you have it. You will deal with this quite a bit in homework 3, right? So there will be at least one question on this in homework 3. So imagine that you have your data, right? You have your x's, right? You have their x in here, and now sometimes I don't know if let's say you have 3, 4, 5, 6, 7, 8, 7, 8, right? This is your x. This is your capital X. So now you can see basically in here, you have dependency. You have 2 columns, right? They depend on each other, right? So there is linear dependency in here, right? But remember, what we are really doing in the normal equations, we're taking the x transpose times x, and then we take the inverse, right? So if you do this for this one, you'll have singularity issue, right? So what we do, which is a very, very common practice, and you will deal with this at least in one problem in homework 3, is you apply basically your SVD decomposition, and then you look basically at the coefficients in here, which ones are really very, very small, very close to a 0, right? And then basically you eliminate the corresponding column and vector in the U and the V, right? So basically, another way, you are really eliminating any of these singularities from your data, and then you do the decomposition here, right? And now this becomes your x. So now without anything in the orange in here, it means I'm removing it. Why I'm removing it? Because in my coefficient in here is very, very small, very close to a 0. That's basically I'm trying to remove one of these, right? So I will have this. That's one way to do it. Now, when you have a small data set, the likelihood of this happening is high, right? If you have very large data set, the likelihood of this happening is very, very small. So if you deal with a very large data set and you do without doing SVD, most likely you will be able to find the inverse and the solution will be fine. But if you are dealing with a relatively small data set, most likely you have such issue there, right? And then when you do the inverse, you'll start to realize, oh, there's something not right, right? This is what's happening. So it's a good practice, and we'll make sure you have the code for it in homework 3 to really do this before you apply your normal equations solutions. Because this is a very common problem when you have small data sets. Okay. Okay. The next thing is in linear regression. So what happens if you have linear dependency? The next one is what if you have multi-output regression, right? Multi-output means what? My y's, right? My yi is not scalar. Remember? I never had y as a boldface, right? Always I had my y as a scalar value, right? Just a value, right? But now what if I have y as a vector? So now my output in here, yi, right, is boldface small. It means it's a vector. It has dimension of k, right? Capital K in this case. So now each one of the y's is not a scalar value, it's not a single value, it's a scalar. So now the first one, I have y11, y12, y1k, meaning multiplying theta 10 plus theta 11 times x11 all the way to theta 1p times x1p will not be equal to y1. It will be equal to y1 1 plus y1 2 plus and so on, right? So there will be multiple of these values in here. So in that case, basically, what do I do? It's the same formulation. Nothing really changed much in here. The only difference in here, I will not really have small y boldface. This will be a matrix in here, and that matrix is what we have in here. So each row is the output for sample one. The second row is the output for the second sample. The kth, this is the nth. The nth row is the output for the nth sample, right? Nothing changed on the right-hand side, right? Nothing changed on the right-hand side in here because my output is a vector or a multi-output in this case, right? So same equation, same everything. The only difference will be in my output. Okay, this is something you will deal with as well in the homework. Yeah, I want to talk about the applications. There's quite a bit of different applications, name it from geophysics to medical data to normal data, text. I have a lot of applications deal with regression. Any question? Yeah, regression. What we did today is extremely important for the next 2-3 lectures. It's very important to remember where we start, what we assume on the way, where we are at the end. Any question about what we did today? Okay, so the next thing we'll do is, what if I have nonlinear data? So we'll have remember the kernels that we imposed last time. Now we had the polynomial regression. So we'll add some polynomials to the mix, and then we look at ridge regression, and we call them regularized regression. What kind of regularization? What kind of things we add to this thing? What kind of conditions we impose in this one to give us a better solution? And we'll see examples of what that we mean by better solutions. If we have a regularization, remember what we have a constraints on the thetas, right, as we solve for the problem. And then we'll end up with some evaluation metrics. So homework 3 will be regression. So we will post it on Monday. Okay. All right. We'll see you Monday. Don't forget, we have homework 2 due this Friday. Remember, please read the instructions. If I give you an extension after 8 p.m. in writing on Piazza, then you have an extension. And I rarely give extension unless you read there's a good reason. If you submit after midnight or Friday night, you'll get a 0. So Celine basically, because that's in the instructions, late submissions are not accepted. And Celine basically in the first homework, he gave 20% reduction, I think, for those who submitted after midnight. But for this homework, it will be a 0. Okay, so please keep that in mind. Whatever you have by 8 p.m. on Friday, just submit it. Thank you. Just give me a second.